So let's dive in. And we're going to start right at the beginning of the movie, where we saw these words, 600 kilometers above the Earth, which happens to be where the Hubble Space Telescope is, so that's correct. The temperature fluctuates between very hot and very, very cold. So, is this right? Of course it's right, it's one sentence, they wouldn't get this wrong, would they? But I'm mentioning it because it gives me a way of bringing up how weird temperature is in space. This is one of the things you have to learn to think about completely differently when you're operating in a vacuum or near vacuum. So, let's talk about the atmosphere. This is what our atmosphere looks like. It's arranged in many, many layers. For those of us who live close to the surface of the Earth, we know that it starts pretty warm down the bottom and it gets colder the higher you go, right? Right?
Right.
But that's not true. If you get very, very high up, you get up to the thermosphere, is the bit we care about. It's up here. This goes, depends who you talk to. For these purposes, it goes up to where the Hubble Space Telescope is. It's called the thermosphere, I assume, because it's hot. It's way up in the outer layers of the atmosphere. It's the first bit that the sun's energy hits. The atmosphere here is extremely thin. So you haven't got nice air molecules like we have around us. You have single atoms. They've all been ripped apart from their molecules. They have their electrons stripped off them by the energy from the sun. And they're very, very spread out, very, very far apart. Now what this means is they can't cool down. If you want to cool down, and you're an atom, you need some way of releasing energy. So you can do this if you're in a molecule, you have a buddy, you can transfer energy between you. You can do it if you're surrounded by friends, you can bump into your friends and remove energy that way. But if you're a lonely atom, all alone, too far apart from the other atoms to bump into them, you're never going to cool down. So they get hit by the sun, they get very, very hot, they can never cool down, so it's thousands of degrees up there. Really, really hot. So am I saying this statement is wrong? No, because this is how we need to think about temperature differently. The atoms in the upper atmosphere are extremely hot, but if you put your hand out there, don't put your hand out there, if you put your hand out there, it would feel very, very cold, because there's no way of that energy transferring to you. The air is too thin, those atoms are unlikely to actually hit the surface of your hand, and so the air feels very cold. So what we're talking about when we talk about it fluctuating between like plus and minus 200 degrees, this is the energy you would feel from the sun. When you're on the day side of the Earth, you're being bombarded by the sun, you would get extremely hot. And when you're on the night side, it will be extremely cold because there's no atmosphere retaining any of that heat. So this is the kind of stresses that things like the Hubble Space Telescope have to be able to withstand. They have to be able to go from plus 200 to minus 200 degrees without breaking apart, which is pretty cool. Okay, so next line. There is nothing to carry sound. This, again, seems like a no-brainer, right? But this is how nitpicky I am. Technically, I just told you that they're still in the atmosphere. It's a very, very thin bit of atmosphere, but it's not zero. In fact, there is no such thing as a complete vacuum in space. So we all know how sound works, right? You have a bunch of particles in the air, and as they vibrate, they pass on energy. So if you look at these particles here, you can see the wave, that's a sound wave, propagating from left to right. If you're an individual particle in that air though, there's a few highlighted in cyan just to make it easier to watch one individual particle, they don't move. They wobble back and forward a little bit, but on average they're not moving. So the energy is being transferred left to right, individual particles stay pretty much stationary. This only works, of course, because these particles are very, very packed together and they can transfer energy between them. If you're way up in the upper atmosphere, or way out in space, even in deep space, there's about 1 atom per cubic centimetre, you're not going to be able to pass that energy on unless you have a really, really long wavelength sound. So a very, very, very deep pitch sound, way deeper than any of us can hear, you would actually be able to transmit sound in space. But fine, for our purposes, sound we can hear, no, there's nothing to carry sound. So we then hear there's no air pressure, no oxygen. Again, I'm going to say no is a strong word. There's a little bit of air pressure. I mean, you're not going to care about that when you die, but again, there's a little bit of oxygen up there, but not enough to keep you alive. We're then told life in space is impossible, and this one I will give them without caveats. It's at least extremely difficult without assistance, as we saw in this movie. So let's talk about this movie. We're joined at the beginning of this movie, the mission STS-157. If you follow the space shuttle missions, you immediately know this is set at some indeterminate time in the future. It's this cool parallel universe where the space shuttle program kept going. In our bad timeline, the shuttle program stopped at STS-135. So there's been another 22 missions since the last one that happened in our universe. This one is going to service the Hubble Space Telescope, which is pretty cool. I care about that. And there have been a bunch of missions servicing the Hubble Space Telescope, 5 to be exact, not counting the one that launched it. It was launched on the 24th of April 1990 aboard the Space Shuttle Discovery. And then it opened up, people started looking at the images and realized, oh, we did something wrong. There was a fairly major flaw in the optics of the telescope, and so Service Mission 1, which launched on Endeavour on STS-61 in 1993, December 2 to 13. It did a bunch of things, but the main thing it did, the really exciting thing, is it fixed the flaw in the optics of the telescope. And here's a nice before and after picture. The before is what we were stuck with when it first launched, and then after putting in a little tweak, we get bright, shiny images. And this is what's enabled us to use the Hubble Space Telescope to do awesome science and also create some of the prettiest pictures we've ever seen of space, which is really, really cool. But that wasn't enough. The cool thing about the Hubble Space Telescope is it's really old technology, right? It launched in 1990, but the ability to go back and keep updating it means we've been able to keep doing really, really awesome science with it. So that brings me to Service Mission 2, which was in 1997. This was another Space Shuttle Discovery, which is the shuttle that has visited the Hubble Space Telescope the most. And this again did a bunch of things, but the thing that I really care about is it installed a new camera called NICMOS, which extended the range of light the Hubble can see into the near infrared. Near infrared, if you've ever seen me talk about science before, is really, really cool because it lets you see galaxies that are very, very far away, where because of the expansion of the universe, all the light has been redshifted out of the optical range of the spectrum into the near infrared. It also lets you see a little bit through dust, which is really helpful. So this example image I showed is a star cluster right in the galactic center, where dust obscures a lot of the light, but you look in the infrared, lo and behold, there's some very, very pretty stars. Service Mission 3 was another discovery mission, but it ended up being split into 2. There was a Service Mission 3 that was planned, and then disaster struck. Hubble Space Telescope has 6 gyroscopes on it, which is what enables it to point in the right direction. And it can operate with 3 of them, and by the beginning of 1999, 3 of them had failed. So it was really on its last legs. And so it was decided that Service Mission 3 would be split in 2 halves. So Service Mission 3A launched in December 1999. About 3 weeks before the mission launched, a 4th gyroscope failed. So it's really, really lucky that they split these 2 apart. It meant that Hubble actually had to close for several weeks. It couldn't do any observations until this repair mission went up over Christmas and repaired the telescope, which was the best Christmas present any astronomer at the time had. So these are a picture of Hubble with the gyroscopes, which are now working much better than they were. So 3B took another few years to get off the ground. It launched on Columbia, STS-109 in March 2002. And it again did a bunch of little repairs and things, but the most important thing from my point of view is yet another new camera. This one operates in the optical range of the spectrum, but was much better than the old one. It's called the Advanced Camera for Surveys, and it's responsible for most of the really pretty optical images that you've seen from the Hubble Space Telescope. So there was one last mission to the Hubble Space Telescope, and that's Service Mission 4, which was actually the 5th one. And it's the one that's the nearest and dearest to my heart because it installed some boring ultraviolet instrument. The person who worked on that instrument, by the way, couldn't be here tonight, so I'm allowed to say that. She does work at UT, was there for the launch. This went up on the Shuttle Atlantis on STS-125, May 11 to 24, 2009. And as well as installing a boring ultraviolet instrument, it installed the Wide Field Camera 3, which is the instrument I do most of my work with. It's the instrument featured on my dress. It can actually see in the ultraviolet as well, but I don't care about that. I care that it can see in the infrared. So similar range to what NICMOS could do, but it's way better, way more sensitive. It's basically completely replaced NICMOS. It's a beautiful camera and has given us some amazing images of the distant universe. This is the thing it does best, the very, very distant universe, the first galaxies, which is what I work on. Every time you hear something in the news about astronomers discovering yet another really, really far away galaxy, it came from this instrument on Service Mission 4. So I was at a conference last year presenting a poster, and who wanders up to my poster but one of the astronauts from Service Mission 4, who now works on the James Webb Space Telescope, which is going to be the successor to Hubble. And I'm trying very hard, I'm super professional, right? I'm not going to fangirl, I'm going to be really, really cool. So I just stand there, describe my science, and then he wanders off, and I think, damn it, I should have asked for a selfie. I should have just been a fangirl, because who cares, right? Anyway, sadly, Service Mission 4 was the last service mission to the Hubble Space Telescope. Not long after that, the Space Shuttle program was cancelled, because apparently it's more important to spend money bombing people. Who knows? So, Hubble Space Telescope. It's way up there, 600 kilometers, about 350 miles above the Earth. It does orbit the Earth roughly every 95 minutes. So that number should be ringing a bell, having just seen the movie. It's traveling about 17,000 miles an hour. And question number one, is there gravity in space? Yes, of course there is. You're all nerds, you know this. Of course there's gravity in space. If there wasn't, nothing would stay in orbit around anything. That all depends on gravity. When you're in orbit, you're essentially in free fall. So you're feeling the gravity of the thing beneath you. You're moving very, very fast. And what happens is you're moving so fast that as you fall, you keep missing the Earth. So the Hubble Space Telescope is traveling very, very fast. It's falling all the time. So if you're up there working on the Hubble Space Telescope, you are also in orbit around the Earth. You're also in free fall. You're also going 17,000 miles an hour. And so everything cancels out. This is one of the things that Einstein's relativity tells us, is that gravity is basically indistinguishable from acceleration. So if you're falling, it's exactly the same as being in gravity. But if you're falling at the same rate as the thing that you're looking at, it feels like there's no gravity. So relative to what they're working on, they're in zero gravity, but they are actually experiencing gravity. Now the reason I mention how fast the Hubble is moving and what its orbit period is this is science problem number one with this movie. They make a very, very big deal of how this debris is going to come around and hit them every 90 minutes. And a few people actually praised this, a few scientists, on Twitter were praising this, saying, yeah, this is really good because that's actually the orbital period of Hubble. Well, fine, but the satellites that broke up were also in orbit. And we'll talk about which orbit in a moment because that's kind of weird and wrong. But if all that debris was completely stationary, then yes, you in orbit around the Earth would hit it once every 90 minutes. But there is no way it is stationary. If it was stationary, it would just fall straight down to Earth. So the 90-minute thing makes absolutely no sense. Not to mention...
Set your watch for 90 minutes.
Why 90?
Well, Houston clocked that debris at 50,000 miles an hour. If you factor in our current orbit, then I figure we got about 90 minutes before we get our asses kicked again.
So did you notice that George Clooney quoted Houston as clocking the debris at 50,000 miles an hour? That is not what they said. They said 20. 20 would be reasonable for something in an orbit of that height. 50 is not. Neither number makes any sense. If the debris should be moving at 20,000 miles an hour, but it should be moving at the same rate that they are, and so they shouldn't keep encountering it. If it was going 50,000 miles an hour, then it would be shooting off into a higher orbit and it wouldn't be a problem. So let's talk about the orbits of the various spacecraft that we encounter in this movie. We start with HST. HST is around, 350 miles above the Earth. And on this image, it is over here. We also see the International Space Station. That's about 100 miles lower than the Hubble Space Telescope. It's also in a completely different orbit. You can see it down here. It follows the red line. You can see it very, very rarely crosses over with the Hubble. And then we have the Chinese station. The Chinese station in this movie is a fictional future version. It's way bigger than the current Tiangong. But the best I can do is show you the current Tiangong, which is over here, following the blue line. And so you can see there is no point where all three of these things should be within sightline of each other. There is no point at which this movie should have been able to work. Unfortunately, despite her best efforts, Sandra Bullock should have been stranded up there. But you know what? This is a fictional other timeline where the space shuttle program kept going, and maybe in this better timeline, they decided, hey, maybe we should put all these things close together so that if disaster happens, we have escape pods. Who knows? Let's run with that. It's more fun than hating the movie. But complicating things a bit more is the fact that all of these three things, despite being around 100 miles apart, are all in low Earth orbit. So this is a to-scale diagram of the orbits. All of these things are way, way down here. The communication satellites have to be in a geostationary orbit, which means they have to be above the equator, far enough away that their orbit exactly matches the rotation of the Earth. 24 hours is much, much longer than 90 minutes, so they have to be further away. In fact, they are much further away. They are way out here. So when they talk about debris from, we don't know where the spy satellite is, obviously, that they blew up because it's a spy satellite, but the debris somehow hits the Hubble Space Telescope and the ISS and everything, which is way, way down here, and it takes out all the communication satellites, which are way, way, way out here. This doesn't make any sense. I mean, it helps the tension of the movie that no one can communicate, but it doesn't make any sense. But let's talk about something else that they did well. I told you to think about Newton's laws. Newton's first law of motion. Any object at rest or in a state of constant motion will stay in its state of rest or constant motion unless acted on by another force. One of the first times we see this in action is...
Do it now! That's right!
So, Sandra Bullock unhooks herself. She gets flung in the direction that she was moving at the time. She was on a big rotatey thingy. And because she was spinning, she keeps spinning, and she keeps spinning, and she keeps spinning, and it's really nauseating to watch, right? And that's exactly right. There is air, but there's very, very little air, not enough to cause noticeable drag. There's nothing to slow her down. So left to her own devices, she will keep flinging off into the distance. She will keep rotating, keep feeling increasingly nauseous forever, unless she's rescued by George Clooney. Which luckily she is, but then she doesn't return the favour. So let's talk about the big question. This was the one that caused the biggest arguments when this movie came out. Did George Clooney really have to die?
Gotcha.
Sandra Bullock has her feet caught up in the parachute cord things. George Clooney is on the end of the tether. George Clooney gets flung out. The tether goes taut. He stops. What forces are acting on him at that point? None in his rest frame. He's still in orbit, whatever. In his rest frame, there are no forces acting on him. He has stopped. If you want to pull him back in towards the ISS, all you have to do is give that tether a little tug. He'll start floating towards you. Problem solved. George Clooney is saved. It was completely unnecessary for him to unhook himself. And I assume the reason this is in there is first of all to get rid of George Clooney, which frankly I'm all in favour of in this movie. He's incredibly annoying and unprofessional. But he really should know a bit more about how space works. He's supposed to be the veteran astronaut in this movie. It's designed to look like, you know, those scenes you get in every action movie where someone's hanging off the edge of a cliff and someone's holding their hand and they're saying, "Don't let go," and the person lets go. And it's necessary in those movies because there's gravity pulling them down. This movie, there is no gravity pulling him down in that rest frame, so he should have been totally fine. Like I said, though, I'm not exactly mourning him. So let's talk about gravity. It's the title of the movie. Another thing that a lot of people said when this movie came out is, oh, it shouldn't have been called Gravity because it had nothing to do with gravity. I disagree. I think in many ways gravity is the main character of this movie, even if only in its absence. It's certainly the thing that makes the movie stand out. It's the thing that made it incredibly difficult to film. And that becomes really noticeable in this scene. This is a really cool scene, right? If you're a movie buff, what you're thinking here is, oh, right, she's curling up in the fetal position because this is this whole theme of rebirth and whatever, she's deciding to live. If you're a science nerd, you're thinking, what's going on here? She took off her suit way too easily. It should not be that easy to take off. And then underneath, what is she wearing? I mean, she should have had a whole layer of like thermal stuff on. She should be wearing an adult diaper. I assume they made an artistic choice not to have Sandra Bullock in an adult diaper. So not very realistic. However, the way they pulled off the zero-G effect of her like curling up and floating is really cool. It's not perfect. You can tell that it was shot at a soundstage on Earth. In particular, look at her hair. That's not floating. Her clothes are not floating. But it's still pretty cool. And they did film this in Earth normal gravity. I understand they considered using the vomit comet, but it turns out you only get about 15 seconds, and that wasn't long enough to do all these really, really long shots that they have in this movie. So it's all faked. It's all like rigs. There's obviously a lot of CGI, but this scene is all done with rigs and puppetry, and it's pretty amazing. So I'll give them a pass on that. I think this is really cool. There are some other cool like zero gravity effects that you see when she's in the ISS, including as she's zooming through the ISS, she like pushes something out of the way, and as the camera pans over, you notice that there's something on fire. And this is obviously giving you a hint that things are about to go really, really wrong, which is lucky for the story, because otherwise she would just hang out on the ISS forever. But the really cool thing is these tiny, tiny little flames are spherical, and they're kind of drifting away. And this is kind of what fire looks like in zero gravity. So on the directions right here, we have what a flame looks like on Earth. The reason it has its teardrop shape is gravity. Oxygen is being pulled in at the bottom, it heats up as it's burning, and hot air rises because of gravity. So as the hot air rises, more is drawn in underneath, and it gets drawn out into this teardrop effect, which is entirely because of the buoyancy of hot air. In zero gravity, you don't have that. So you get these spherical flames, where instead of just drawing in oxygen from the bottom, it's grabbing oxygen from all around in this cool sphere. You can see the hottest region, which is in blue, is on the outside. This is a really cool experiment that was done on the ISS. This is a drop of fuel in the middle being ignited by these two things on the side. And as it gets ignited, it blows up, and you get these little spherical flames dancing around, and they like move around looking for oxygen, and it looks like it's alive. It's really, really cool. Okay, but there are some things that they do wrong. There was this really, really deep, heartfelt scene where we see Sandra Bullock crying, where she's saying, "No one will mourn for me, no one will pray for my soul." It's really, really deep unless you're a science nerd, and you're distracted by the fact that there are these teardrops coming off her face. And they've clearly tried to do this correctly. The teardrops are also spheres, and they drift off into space, they drift towards the camera, and it's a really, really cool effect. A lot of scientists actually praised it. Neil deGrasse Tyson praised it on Twitter, but it's wrong. The water has surface tension, so if you cry in zero gravity, it's just going to stick to your face. She should have just had a wet face. A cool thing you want to look up if you want to see that effect is Chris Hadfield on the ISS did a really cool experiment where he wrung out a wet cloth. and you just get this like glove of water enveloping his hand, but it never drifts off because of the surface tension. So something's good, something's bad with the actual gravity. Okay, so we've escaped the ISS. We're trying to get to the Chinese station, and she thinks to take with her a fire extinguisher. This seems like a pretty cool idea, right? Because she clearly calculated her jump really, really wrong, and she would have just gone floating into space forever. But luckily she had her fire extinguisher, so she was able to use that as a thruster and get herself in the right position. So is that realistic? I mean, physics-wise, yes, a fire extinguisher will give you some thrust. In practice, you have to be really, really careful about where you're pointing that thing. Unless you know exactly where your center of mass is, and you're holding it exactly in the right position, all it's going to do is make you spin. And to be fair, like, she has some trouble getting the hang of it, right? She spins around a bit before she goes in the right direction. Unfortunately, fire extinguishers are not that big. She already used it on the actual fire on the ISS. You notice her bring that one with her, and then she grabs it when she's in the Shenzhou, not the Shenzhou, the Soyuz, when she's on her way to the Chinese station. So she would have run out of fire extinguisher fluid long before she actually made it to the Chinese station, unfortunately. But luckily, this is an infinite replenishing fire extinguisher, and so she makes it safely. But the main reason I wanted to bring this up is the exact same scene features in one of my favorite movies, WALL-E. This is a great scene, and I wanted to show it because I really wanted to do a screening of WALL-E, but apparently we can't get rights to do Disney, so I can show you this one scene because it's fair use and it's educational, so there. This is really cool. And again, like, not completely scientifically accurate, but it's WALL-E. Who cares? Alright, so we're now on the Chinese station, and she talks about how it's losing altitude, it's kissing the atmosphere. And this is really a chain reaction thing that just gets worse and worse. If you start slowing down, you're going to lose height. You're no longer missing the Earth quite as much as you move past it. As you lose height, as you slow down rather, you lose height. You hit the atmosphere causes drag, it slows you down, you lose height. You get the picture. Soon you're coming to your splashy doom on the Earth's surface. So this is also another situation where she can't just hang out and wait for rescue, which is very cleverly done. She has to find a way to re-enter the Earth's atmosphere safely. Luckily, the Shenzhou re-entry capsule on the Chinese station is intact, and she figures out how to use it, and that's all great. But I really did like this effect of like the atmosphere running over the tips of the Chinese station, and you see it slowing down, losing altitude. It's really, really cool. And then as she re-enters, she comments, it's getting really hot in here. That's because as you re-enter the atmosphere, there's a lot of friction, you get this huge pressure thing in front of you, and so it does get incredibly hot, and the whole point of these re-entry capsules is to be able to withstand this heat and get you to Earth safely, which thankfully it does, and then she almost drowns. But that would be a really rubbish ending, wouldn't it? Sandra Bullock makes it safely back to Earth. We think, like, we don't see anyone find her. Let's assume she makes it back home to Illinois safely. So she survived this movie. Did physics survive this movie? What do you think? So I actually think it did. It's a bit battered, a bit bruised, a bit scratched up. But they did a pretty damn good job. This was a really, really hard movie to make. And I think it came out really, really well. And yes, I have some gripes, but I have gripes about everything. So it's fine. So next month, we're going to do another movie that I actually think has a pretty good bash at the physics. This is The Martian. We're going to try and rescue Matt Damon for reasons. I don't have a problem with Matt Damon. I don't know why I said that. So Wednesday, May 17th, it'll be the Alamo Drafthouse Mueller, right back here. Tickets, I'm told, will be on sale this Friday. If you're on the Astronomy on Tap mailing list, you'll get an email as soon as tickets are on sale. If not, just check the Alamo Drafthouse website and you'll see it there. We'll also post on Facebook and Twitter and so on. I hope to see a bunch of you next month. We have found that doing Q&A in these theatres doesn't work very well, so I will be hanging out in the bar for a little bit. If you have questions, if you have your own rants, things I wasn't able to cover every science gripe in this movie, so if you have other things you want to talk about, come hang out in the bar. And thank you all very much for coming, and I'll see you next month.